Hello everyone, this is Aidan for Fluid Mechanics 101, and in today's talk I'm going to be talking to you about porous zones in computational fluid dynamics. In this talk I'm going to be going through what are porous zones in a CFD code and when should you use them in your modelling application. I'm also going to look at how are porous zones accounted for in the Navier-Stokes equations and solved by the CFD solver behind the scenes. So you should really get a good idea of what's actually going on in the CFD code when you turn on or use a porous zone. To finish the talk, I'm then going to go on to talk about the coefficients C1 and C2 that you need to apply when you activate a porous zone in your model. We're going to look at what are the coefficients, how are they derived, and how are you going to apply them in your model when you activate a porous zone in your CFD model. So sit back, pay attention. I know you're going to find this talk extremely useful if you choose to use a porous zone in your CFD model. So just to start things off with some quick examples of some applications where you might consider using a porous zone in your CFD simulation. You can see from the figures there I've got on the screen, we've got some grills and porous walkways which you may see in various industrial settings where you have a mesh walkway which isn't entirely solid. And I've also got some images there of louvers that you'll often see on the outlet of ventilation and air conditioning systems, often to prevent moisture from getting into the building. And then the final application I've got there are tube banks or stacks of horizontal cylinders or closely packed items. And all of these applications are fairly typical of places where you would often consider using a porous zone in your CFD model. But they're not the only places where you would use a porous zone in your CFD model. So how do we choose when to use a porous zone and when to not use a porous zone? The thought process that you should be adopting when you're setting up your CFD simulation is that normally the entire geometry should be meshed. And what that means for a typical application with louvers or gratings or any other CFD geometry is we mesh all of the flow passages where the fluid is expected to travel. So what that will mean is generating a mesh between all of the fine holes and gaps between the gratings, the grills, the louvers, or whatever application you have. Now, for some of these applications, like if you have a very fine grating or a very fine grill, that means that the mesh which you would generate would be extremely fine and in some cases would be poor quality or drive the cell count too high. And it's under these situations where when the mesh is too fine to be practical to fit through all of the gaps, then we would consider using a porous zone instead of meshing the actual geometry. So always remember that when you're setting up your simulation is that the first priority should always be to mesh the entire geometry. However, if you can't generate a mesh that's sufficient, then consider using a porous zone instead. Now, before we look at how the porous zones are solved by the CFD solver, we first need to think about the physics of what's happening when a fluid flow encounters an object like a grating or some louvers. What I've got for you on this side is a simple example problem for you to think through, which will help you to understand how porous zones work. So if you consider the flow passage there, which you can see on the screen, with the flow going from left to right, from station 1 to station 2, and the flow passes through a porous zone in the middle, which is highlighted in dark blue. Now, this flow passage has a constant area. So the area A1 at the left is equal to the area A2 at the right, which is also equal to the frontal area of the porous zone there in the middle. Now, if you apply a continuity or mass conservation argument, then you know that rho, the density, times U1A1 is going to be equal to rho U2A2. Now, because the areas are the same, then we know that, at least for an incompressible flow scenario, that U1 must be equal to U2. So the volume averaged velocity at the inlet is equal to the volume average velocity at the outlet there. Now, there may be some mixing and some fine flow structures generated from the porous zone, but the volume average has to be the same. And what that tells us physically is that the porous zone, as an obstruction, doesn't remove kinetic energy from the flow. However, the porous zone will still remove energy from the flow, and the way we do that is removing energy from the flow as a pressure drop. Because we can't remove kinetic energy, so we're removing pressure energy from the flow. Now, in general, we don't know exactly what the pressure drop will be. However, experimental measurements tell us that the faster the flow velocity going through the obstruction, the greater the pressure drop. And based on that physical reasoning, we can come up with equation 1, which says that the pressure drop across that obstruction is going to be some polynomial function of velocity. Now, we could choose any function we wanted, but it's commonplace to choose a polynomial function of velocity. So as velocity increases, the pressure drop across that porous zone increases. And in the majority of applications, we only consider the linear and quadratic terms in that polynomial function. And it's also commonplace, you'll see for porous zones and also for porous jumps, that the quadratic term in C2 is written in the form of a dynamic head there. So you can see going from equation 1 to equation 2 that C3, C4, all the higher order coefficients are set to 0. And for C2, we've included a half rho there in front of the velocity. So it takes the form we usually expect to see for a dynamic head. Now, it's very important at this stage to carefully consider the choice of velocity that we use in that polynomial. Now, if we consider this flow passage where the porous zone only occupies a fraction of the width of the flow passage, then you have U1, which is the volume average velocity across the entire flow passage, and we also have U, which is the volume average flow velocity across the porous zone itself. And it's very important that the velocity we choose in the polynomial expression for the pressure drop is that local velocity U and not the volume average velocity over the entire flow passage, U1. And this distinction is fairly important later when we derive those coefficients C1 and C2 to make sure that the coefficients we put into our simulation are correct. It's also worth noting that the velocity we choose is not the superficial velocity. Now, to understand what the superficial velocity is, what you need to do is zoom in and think of the flow between the gaps in that porous obstruction, as you can see there in the diagram. Now, the flow will approach the porous obstruction with a velocity u, and now between the gaps, because the area is reduced, the velocity will increase locally. And this local velocity through the porous medium is called the superficial velocity, us. And it's greater than u because the area is smaller. Now, it's very important that the velocity we choose for the pressure drop expression is that approach velocity u, which we see there, and not the superficial velocity through the gaps. Now, how is a porous zone accounted for in the Navier-Stokes equations, and how is it solved for by the CFD code? Well, I've got for you there in equation 3 the Navier-Stokes equations, and what we do to account for the porous zone is we add a source term to the right hand side of the Navier-Stokes equations, S. Now, it's very important that we note this, that it's a source term and we're not adding a pressure drop to the Navier-Stokes equations. So at first glance, you may think that the pressure drop from the porous zone will be incorporated into the pressure gradient term there in equation 3, but that's not the case. The way that porous zones are accounted for in CFD codes is by adding an additional source term S on the right hand side. And how the source term will work is the source term is 0 in all of the cells in the mesh that are not in the porous zone. However, for those cells that are in the porous zone, we have a contribution to the source term S there. And also important to note that this source term is applied at the cell centroids for cell-centered finite volume CFD codes like OpenFOAM and ANSYS Fluent, for example. The source term is applied at the cell centroids there. So we know what the pressure drop will be across our porous zone, but what is the source term going to be that we add to the Navier-Stokes equations? The first thing to note is that source terms in general in the Navier-Stokes equations have units of force per unit volume. Now, this is common across all transport equations that you may solve. For example, the energy equation, the source term in the energy equation will be energy per unit volume. And the reason it's per unit volume is because this source term will be multiplied by the volume of the cell locally that we're solving. So we need to derive a source term which has units of force per unit volume. So a force, of course, will have three components. In a Cartesian system, this will be x, y, and z. And just for simplicity here, I'm going to just look at the x component, and you can do the same for the y and z components if you wish. So starting with the pressure drop in the x direction, that's equation 4, then the force will be the pressure drop multiplied by the frontal area of the porous zone. So that's the area that the fluid encounters as it hits the porous zone. And of course, remember, we want the force on the fluid and not the force on the solid. And so we add a minus sign there in equation 5, which is the force. And then to get the source term, we divide the force by the volume of the cell V. And so we arrive at equation 6 there. And equation 6 is very similar to the pressure drop, except that we have a 1 over T there, which is the thickness of the porous zone. And the reason we have this is because we've taken the frontal area of the porous zone and divided it by the volume of the porous zone. So that's the thickness of the porous zone. And it's very important to note here with equation 6 that T is the thickness of the porous zone in the direction of the flow that we're considering. And don't worry if you don't follow what that is at the moment. I'm going to show you in the next slide so that you understand. So the image on the left there shows the thickness of the porous zone if the flow is in the x direction. So you can see the flow there is from left to right, and the velocity will encounter that frontal area of the porous zone there, and the thickness T is the thickness in the direction of the flow. Now, for the y component, if the flow were to approach the porous zone from the top down, then the thickness this time would be the thickness in the direction of the y flow there, which you can see as top to bottom. Now that we understand this treatment, what we see is that there's a problem generated for the CFD code, which is the CFD code doesn't know the overall shape of the porous zone. It may know the local thickness of the cell, however, it doesn't know the thickness of the porous zone because there may be 3 cells across the porous zone, there may be 10, so the CFD code does not know the overall shape of the porous zone, and so we have to do something clever so that we can still apply this source term to the Navier-Stokes equations. And the way we do that is by bringing that thickness there, 1 over T, inside the source term and combining it with the coefficients C1 and C2. So we haven't yet specified what C1 and C2 are, but what we're going to do is divide them both by the thickness of the porous zone in the direction of the flow. So for the source in the x direction, it's going to be the thickness in the x direction. For the source in the y direction, it's going to be the thickness in the y direction. Now, before we carry on, it's worth pausing for a moment to be very careful and consider the units of these coefficients before we start deriving them. Now, looking at those two terms there, the second term, remember, with C2 takes the form of a dynamic head, which is a half rho u squared, and that means C2 would have no units. It would be dimensionless. So if we divide C2 by the thickness in the x direction T, we see that C2 over T has units of 1 over meters. Now C1 is a little bit more tricky because U has units of velocity, meters per second, whereas the source has units of force per unit volume. And with some playing around with units, which I'm not going to go through here, you can easily do it by yourself if you want to, we find that C1 over T has units of kilograms per meter cubed. So what we're going to need to do now is find a way of specifying and deriving these coefficients and being very careful to ensure that they have the correct units. When we have these coefficients, we can apply them to the CFD code, C1 over T and C2 over T, and that will allow the CFD code to compute the source term locally in the cell that it will then apply to the Navier-Stokes equations. So now we're going to have a little bit of a more deep look at each of those coefficients, and starting with the coefficient C1, the first thing we do is have to take a look at Darcy's law, and you may see Darcy's law talked about in user manuals that use porous zones. And what Darcy's law states is that for flow through a porous media or a media with packed solids in the direction of the flow, if the flow is a low Reynolds number, so it's a very slow laminar flow, then the pressure drop there is linearly proportional to the velocity u, which you can see there in equation 10. And that's the direct form of Darcy's law. If we compare Darcy's law directly with the pressure drop relationship we used earlier, that's equation 11, we can compare the terms and see that actually C1 over T, which is one of the coefficients we're going to be specifying, could alternatively be written as mu over alpha, where mu is the dynamic viscosity of the fluid and alpha is the face permeability, which I'm going to come back and look at later. So what this is telling us is that we could apply C1 over T to our CFD code, or alternatively, if we knew what mu and alpha were, we could use those and apply those to the CFD code instead to calculate C1. So just a quick recap here for deriving the coefficients. When we use a porous zone in our CFD codes, we have to specify C2 over T, which has units of 1 over meters, and then we can either specify C1 over T, which has units of kilograms per meter cubed, or mu over alpha, which also has units of kilograms per meter cubed. But how are these coefficients calculated or derived? What if you had a physical grating or set of louvers on your CFD application and you wanted to know, I'm going to apply these as a porous zone, how do I get the coefficients? What are the coefficients? What numbers do I put into the CFD code to ensure I get an accurate solution? Well, it turns out there are two methods which we can use to derive these coefficients. And the first method is using empirical data. So for some components, particularly filters, which you may see in some industrial applications, manufacturer's data is often available for the pressure drop across the component with velocity or flow rate. And what you'll often see is you'll get a series of data points from the manufacturer's data, which you can see there in the sketch that I've provided. You've got the manufacturer's data, and then what we can do to that is do a polynomial fitting exercise on the data points, and then once we have our polynomial, we can extract the coefficients C1 and C2 from that. So for some components you may have empirical data and you can do this. The important thing to remember if you're using empirical data is that after you've performed the curve fit for pressure drop against velocity, you've calculated C1 and C2. However, for the CFD code, remember, we need to apply C1 over T and C2 over T. So what you would then do is you'd want to measure physically how thick is your obstruction or your grating or your louvers in the flow direction and divide the coefficients by that thickness so you apply the correct source terms to your CFD code. Very important to remember to do that. Now, in some codes, like ANSYS Fluent for example, that ANSYS Fluent doesn't give you the option of applying C1, and it will give you the option of applying alpha directly. Now, if we think back to where we've got equation 15 there, remember that C1 over T is equal to mu over alpha from Darcy's law. And if we rearrange that, we get that the face permeability alpha is equal to mu, the dynamic viscosity of the fluid, divided by C1 over T. So you can see that if you did do the curve fitting exercise there, what you would do is you'd now have your coefficient C1 divide it by the thickness of the medium, and then you would divide the dynamic viscosity of the fluid by that coefficient, and that would give you the face permeability, and you'd apply that face permeability to the model in Fluent. Now, that may seem confusing at first, but it's important to remember that all you're really doing here is specifying that linear coefficient C1 there. And as always, one of the main takeaway points from this talk is to be very careful with the units that you apply when you're specifying your coefficients. So the face permeability alpha there has units of dynamic viscosity divided by C1 over T, and if you work that out, you'll find that the face permeability has units of meters squared, which may not be intuitive at first, but if you use the fraction there in equation 15 with the correct units, you'll ensure that alpha also has the correct units. Now, the second method of calculating the coefficients is to use data from textbooks. Now, in some textbooks, there is empirical data available for a variety of components, and one such component which you'll often see is a porous plate or a porous disc there. And in the textbooks, what you'll find is that the head loss coefficient K is given as a function of some geometric parameters of the object there. So in the case of a porous plate, you can think of the porous plate being specified in terms of its open area ratio. So that would be the open area of the flow, which lets the flow through, divided by the total area of the plate or disc. And in the textbook, you'll often find a graph like that, which you can see on the slide. And what you would do for your application is look at the physical geometry that you have. How much open area does my porous plate or disc have? What's the total area? Divide the two, and then you can read off the empirical data there from the textbook, and that will get you your head loss coefficient K. Now, if we compare equation 17 with our pressure drop equation that we saw earlier, we can see that K is actually equivalent to C2. Now, this is why you may see the two different notations used. K will be the head loss coefficient, and C2 will be the empirical parameter that we use for fitting. Once again, I know I've said this before, but once you calculate K or C2 by reading it off the graph, you then have to once again divide by the thickness of the medium. So in this case, the thickness of the plate, to ensure that you have C2 over T and that it has the correct units. So the method you use to derive these coefficients C1 and C2 will vary depending on your application and what data you have available. The last thing I'd like to do to wrap up this talk is to think about 3 dimensions. Now, when we apply this porous zone to a region in our CFD mesh, in our CFD code, we generally have a 3-dimensional flow and a 3-dimensional solver. And what that means is that the source term will be applying sources in the X, Y, and Z directions. So we need sources for X, Y, and Z, and that also means that we need coefficients, C1 and C2, in the X, Y, and Z directions. So we're going to need a total of 6 coefficients per porous zone that we have. And if we think about the physical geometry of a lot of these components that we'll be using, in some directions the component will be fully solid and won't let any flow through at all. So if you look at the sketch I've got for you there on the slide of a porous walkway or a porous grating, what you'll see is that the grating will allow flow through in the Z direction, top to bottom, but in the side directions the grating is solid and won't let any flow through. And so what we would do for these directions is set the coefficient C2 as a very large parameter, say 5,000 or 10,000 per meter, tends to give stable results. And what that will do physically, if we think about it, is the source term S will be a very large negative number. So that means we have a very large momentum sink in our flow field. So any flow that's coming in and impacts the porous zone will have all of its momentum removed and will end up being stationary in the X and the Y directions there. So the porous zone will behave like a solid wall in the X and Y directions. And in this case, in the Z direction, we would use the calculations that I just went through to calculate the coefficients C1Z and C2Z so that the porous zone lets through the appropriate amount of flow in those directions. And you'd have to repeat this for every porous zone that you have in your mesh, making sure you get all 6 of those coefficients and that you set a large parameter for directions where the flow is physically blocked by the porous zone. And of course, if you set a very small number, that would mean there'd be no obstruction to the flow at all in those directions. So just to finish off with a quick summary of what I've talked about today, for fine obstructions, remember that the first priority in our CFD code is to mesh the geometry as much as possible. And the reason for that is the mesh will allow us to pick up the fine details and the fine structure in the flow field. However, where it's not possible to mesh our geometry, say in the small gaps between louvers and gratings and tube banks, we can use a porous zone instead. And for those porous zones, we have a coefficient C1 and C2, and we need to specify those coefficients in all 3 directions to give us a total of 6 components. And there are 2 ways we can use to derive those coefficients. And the important thing to remember is once we've got them, we have to divide by the thickness of the medium T in that direction to ensure that we get the correct units. And finally, for solid walls, or in the direction where the porous zone is not porous and is fully solid, it's typical to set a large but finite value to block the flow in that direction. So that brings us to the end of the video. If you found it useful, go ahead and leave a comment in the comment section below. I do try and get to all the comments as quick as I can, and I do really appreciate hearing all the help and support from you guys. It really does help motivate me and grow the channel. And if you found this talk particularly useful and you'd like to say thank you or find a way to give back, there are a number of ways you can do this. You can either leave a donation through PayPal or even just buy me a coffee to say thanks for this video if you found it particularly useful for you. In addition, you can also go ahead and follow me on Patreon, and there are a number of benefits you get to becoming a patron for my channel. The first thing you get is all of the lecture slides that I produce here on YouTube. I upload to Patreon, and you can get those for free if you become a patron. And in addition, you can also get access to my CFD Fundamentals course, which really dives into a lot more detail behind the scenes of CFD codes and is perfect for beginners or if you're looking to brush up on the fundamentals of your CFD knowledge. And all of my patrons get that course for free. And alternatively, if you'd like to pick up a copy of the course or just see what it's like, take a free sample, then head on over to my website, and the link to that is in the description below, where you can get a free trial version of the course, see if you like it. I know you'll find it fantastic, and it will really help improve your deep knowledge of CFD codes and give you confidence in all your CFD applications. That's about it from me. I look forward to hearing from you, and I'll see you in the next video.